professional, these Taunton Press people. All right, I guess we're back. I hope you all partook in your Bloody Marys. I see some of you are still working on your third. Yeah, it's and a great Advil chaser is always what's needed. Yes, very good. The winter camp crowd is just about as good as the summer camp crowd. I can see this is all good news. So we're going to production of heat and cool, because eventually I'm going to turn the production of heat and cool, then we're going to talk about the distribution of heat and cool, then we're going to talk about domestic hot water, and then we're going to try and tie some of this together. But as I warned you, it's all going to be kind of circular, because you have to think of all of these at the same time depending on what's constraining your project. So the traditional way of making heat was something called a boiler. And in the good old days, when people died at 40 with no teeth, we would literally boil water, steam would spread out in pipes and condense in radiators, and the colder the radiator was, the more you get condensation, right? Because water vapor condenses. And it was a wonderful system in the sense that, well, steam would go where the cold spots were, and you didn't need a pump. There was no variable speed drives. In fact, there was no freaking electricity. And so that's why they had to do this. And so steam would go to the cold spots, condense, and then it would come back to the boiler using this technique we call gravity. And one of the features of gravity is that it's absolutely reliable and requires no energy input by us. So it's all kind of like gifts from God and all that. And so that was actually not a bad system, although even then it became difficult to control. We tried valves and stuff. But that's why we called them boilers. We don't boil in boilers anymore, right? In fact, there's usually 2 to 3 safety mechanisms built into boilers today to prevent them from boiling. Because if they boil, you will actually make steam, and that creates pressure. And if you have pressure that's not resisted properly, it explodes, and then you end up with scalding and dead people. And so when I mention back to safety, major issue is not to forget the days when we had exploding boilers and exploding pipes, and you know, it was pretty dangerous stuff, okay? So the reason we don't have that problem anymore is we don't boil water anymore, hallelujah. Modern boilers heat water to somewhere between 95 and 190 to 200 degrees Fahrenheit. We try and stay away from 200 because you might get close to boiling, just to stay away. And although they heat water, people still call them boilers, not water heaters. Although the language is getting blurred, right? You may have noticed that you can use a water heater to heat your space. But that's what a boiler does. The other way that has become universal in North America as a way of heating a space, is to heat the air via a furnace. And a furnace basically is just something that heats air, not water. That's all. Boiler heats water, furnace heats air. And we heat the air. If you're talking combustion, it's pretty rare to have a temperature under 110 degrees, and it's usually verboten to have a temperature over about 140 or 150. And the reason that they limit the maximum temperature is they don't want to cause burning of things that are in contact with the ductwork, like electrical wires and such. And they also want to minimize the stresses on the mechanical system that makes hot in a furnace. We use an electric fan to move the air around. In boilers, we use electric pumps to move the water around. So in both systems, we generally need electricity to make them run, because they have to move the air or the water respectively. Now, in both cases, what we're doing is we're taking heat from a flame and converting it to heat in a fluid of air or fluid of water. The efficiency at which they do that transfer is actually really rather good. It's in the high 90s. All the time is the ability for us to extract heat out of the flame. The problem is that in many systems we throw a lot of heat up the chimney. See, if you don't burn the gas or the oil cleanly, you end up with pollution. And that pollution clogs up pipes. And so you have to clean your chimneys. So they, a long time ago, came up with furnaces that burnt oil, gas, or propane in such a way that it didn't produce much pollution, just because they didn't want to clean out the pipes. The trick is to turn that heat that is therefore generated at 99.8% efficiency into some heat that's useful in the fluid. That's where we've made progress in the last 30 years, is getting the heat into the fluid as opposed to up the chimney. So our fuel sources for boilers and furnaces tend to be natural gas, oil, propane, wood, or electric. Believe it or not, we have electric furnaces that people still build, right? Big toasters with a fan attached. That's what an electric furnace is. An electric boiler is basically a big water kettler with a pump attached. So those technologies exist, although normally not used that commonly because electricity is expensive and polluting. So the most common form of heating a home in America is a condensing natural gas furnace. And it's actually a little bit, the furnace itself doesn't condense. It is actually the exhaust gases. I'll get into. Why are they common? Well, they're cheap, they're reliable, widely available. People know how to repair them, install them. They actually work pretty close to their rating condition when they're operating. Remember I said that we rate air conditioners at 80-degree return air temperature? Well, we don't rate furnaces at that. We rate furnaces at 70-degree or something like 68 to 70-degree return temperatures, which is very close to real life. And their efficiency, if they say 95% efficiency, it's not far off in these modern sealed combustion condensing furnaces. It's pretty efficient. The big trick has been to A, specify condensing, 2, specify sealed combustion, and 3, specify efficient fans. So that's basically how you get to efficient equipment that was not going to kill your occupant and will be, will work well. Now, 20 years ago, to say those 3 things was actually an expensive product. It isn't anymore. A condensing furnace at 95% efficiency with sealed combustion and an efficient fan is actually dirt cheap. Depending where you get your landscape supplies, it could be even cheaper than dirt. And so by efficient fans, the normal approach has been efficient fans are ECM motors. Many people will know that, electronically commutated motors, and there's various brand names for that, or DC motors is another way that's described. But we'll look into how to define what an efficient fan is and how to specify efficient fan. It's basically, make it move a lot of CFMs for every watt you buy. Pretty straightforward. Okay, so this is a common furnace that we would specify, BSC would specify in affordable housing type projects. It's interesting, the rating games here, it's up to 1,200 CFM, up to 46,000 BTUs of gas energy input. And it is $697 if I buy from here. So this is a $700 furnace, which is 95% plus efficient. It actually is 2 speeds, so that it actually, at low fire, it produces about 30,000 BTUs an hour of heat. And it has an ECM motor with about 7 different speeds on it, so I can actually adjust the speeds to be as low as I like, and it uses relatively low electricity if I provide good ductwork. So that's a $700 product that can do all of that. So really, the issue isn't, can I find an efficient, low-cost, reliable, and widely available product? Well, there's one. And how many would you like if you have a big, sprawling house, George? I mean, you could put 7 of those in a house. 10. I can never keep up with these guys because they're always decimals in the wrong spot. So, if you build super efficient homes that are of 20,000 square feet, you will need 8 to 10 of these puppies. Yeah. They're cheap and available, easy to install. Only problem is, of course, 30,000 BTU low fire still is often too much, believe it or not. But this is not a bad option to design for if you have natural gas available and you have a modest size house that has pretty good specs. It's hard to go wrong. And so I mentioned also the price here because, I've mentioned the myth of, well, if I do a really good job on my windows and my wall, I can save a lot of money on my mechanical equipment, right? How much can I save? Up to $700. What the heck? That's like, really? That's the total amount I've got available to save? Like, give me a break. So it doesn't actually, we're beyond that when we're talking low load houses. We're beyond we can save, if you're talking about big homes and making them, or energy inefficient homes and bringing them down to this level, yeah, you can take a $2,000 furnace and drop it to $700. But you can't get any, I mean, $700, for God's sakes, the next step is they're going to be giving them to you. Like, how much cheaper can they make it? iPad plus a furnace? I mean, what the heck? There's no real, room to move. Okay, so if I were to have that furnace that produces 40,000 BTUs of output at a 50-degree temperature rise, meaning return air 70, supply air 120, I would move 750 CFM. And if I were to actually accept, let's say I wasn't working for the Passive House program and I was going to accept warmer temperatures than that, I could reduce my airflow on this unit down to like 650 CFM. And why does that matter? Well, because it means that the duct sizing required to move 650 CFM is relatively modest. So I can, if I take a furnace and I split that 650 or something CFM minimum in half, I'm now down to a main trunk line that's 8 by 12 inches, and that's it. And that's my total, the maximum duct size. Can you imagine a maximum duct size of 8 by 12 inches? Most of the architects are going, no, I can't imagine that. But that is quite conceivable, and that's why getting your flow rates down is useful. And if we need to provide ventilation rates in the order of 80, 90 CFM, I still have to provide ducts everywhere, and the savings between just ventilation and a duct to provide this level of flow is actually not that much. How do they normally price duct cost? The number of actual vents, right? The number of actual diffusers. They'll say, well, $200 a diffuser, something like that. And if you say, I'm going to change the duct size from 5-inch to 4-inch, how much money do they give you back? yeah, a few laughs from the audience. There's no real savings to downsizing the ducts. The savings are getting the ducts small enough that they don't impact the architecture. That's the real saving. It's not that they're going to save a lot of money, because you may be surprised, the cost in ductwork is not the amount of sheet metal. It's the labor to install it and cut it. And therefore, when you shrink the ducts much below this, you don't save any dollars. You save architectural annoyance. So we can run it in a lot of places, and that's worth it. That's worth money. That's worth money. Avoiding hassle of having ducts and drop drywall plenums. A drop drywall plenum costs way more than the freaking duct. So getting around a big duct. So you want to think about, this is simple. Okay. Now, let's say, is Gord here still? Gord Cook? Yeah, there. You mentioned the Trane XC95. So they haven't changed in the last 3 years since I looked at it. So let's say you have a problem with a low-load house. Like Gord can tell you stories to no end. And they'll say, okay, you call up Trane and you say, the problem is every time the furnace turns on in temperatures like this, right? It's 40 degrees outside. I don't need much heat, but I need some heat. The furnace turns on and I just blow the temperature through the roof in the bedroom before it shuts off. Okay, what is Trane's answer? Well, you should use our modulating furnace, our fully modulating, not stage, fully modulating, because it can go way low. But the problem is that the smallest product they sell is a 70,000 BTU an hour furnace, and it modulates down, varies its output until it gets down to 23,000 BTUs. That's one of the lowest outputs on the market. The York actually is lower, because they actually start with a 60,000 BTU an hour product, and they vary at the same 30% down, and then you end up with 20,000 BTUs of output. Carrier, Rheem, Lennox, all have fully variable models, fully modulating models. None of them get lower than 25,000 BTUs an hour. All of these fully modulating products are really expensive. They actually, here's the prices for rough wholesale prices from people who can tell me what it costs, because you can't often get prices, right, unless you actually are a dealer. And so I can't tell you who gives me these prices or I'd have to kill you. But we're in the $2,500 to $3,000, and the Lennox I know is actually even higher. It's $3,500 versus $700. And so the price of getting to lower output is significant. Next problem is this. He said, if I now show up with a furnace that has variable capacity, and it rises up to, in all cases, 60 to 75,000 BTUs, and all these fully modulating, I have to install ductwork that can handle that amount of heat output because it could run at high speed. And so I end up having to put in big-ass ductwork, which is bad, right? B-A-D, big-ass ductwork. So you have to put in this really large ductwork, and then you end up with architectural hassles and no cost savings, etc. And I had to pay several $1,000 premium for the privilege of saving about 6,000 BTUs an hour output over the $700 product. So this is not a technology problem. This is entirely a manufacturing, logistics, distribution problem. People are simply not providing us product we could use. You can buy this product and you can turn off the high fire. You know, there's two valves. That's how these two stages work, right? They have two valves. So you can actually turn off the control for the high fire so it only ever produces 30,000 BTUs at max. That's the cheapest possible solution, and it turns out that it actually is significantly better than these solutions, even though these are much more expensive. Welcome to low-load houses. That's the kind of weird stuff that goes on. And so while it'd be nice to get small furnaces, because I'd like to see a, I don't know, modulating furnace or two-stage furnace with a peak output of 25,000 BTUs and a low of 15. That'd be one model. Another one would be a low of 6 and a high of 15, because then I could actually put them in really quite small ductwork, and I could actually, we're talking like 6-inch diameter supply trunk with 4-inch takeoffs, and you could run that through all kinds of floor joists, knockouts, but even though there's a need for it in the type of low-energy housing we're building, none of the manufacturers are producing it because they have a different point of view. One that you can only get if you have your head somewhere up your posterior. And from that viewpoint, there's no need. So this is a cut out of their technical manual for, this happens to be the train. If you're on 40% low heat, I still need something like 540 CFM. The fan motor is drawing 86 watts, but I have to design for a minimum of 850 CFM, because that would be the least they would allow me. Set the fan on low speed and accept that the minimum airflow that could ever happen would be something around 850 CFM, so my ducts are larger. So I have to pay more for the furnace, I have to live with larger ducts if I want this product that is a low output product. It's not a solution. I mean, it's high tech and sexy and all, but it doesn't solve the problem. So what about boilers? So as you can see, this boiler on the right is so small that Alex has to hunch over just to touch it. And it's called a Munchkin boiler because it's a little Munchkin. I'm sure many of you from around this area know the Munchkin boiler. On the left-hand side, there's an IBC boiler, which many of you won't know. It's a higher tech boiler from Vancouver. One of the nice things about modulating boilers is that many of them will reduce their output to about 1/5 to 1/10 their peak. So they can throttle back more than gas furnaces. Gas furnaces will only reduce their output by about 1/3 of their peak output. So if you buy a 100,000 BTU modulating furnace, it'll go down to 35. Whereas if you buy a 100,000 BTU modulating boiler, it might drop as low as 15 or 11, depending on the product. So the good news there is that you can, and people who install hydronic systems will not insist that the pipes be sized for the maximum output of the boiler, because they know the boiler will itself not run at high load if it can't move the heat. So you can use normal size pipes, and you can actually meet lower loads with products like this. On the left here, we have a Viessmann. There's a number of really good products out there now in the condensing boiler market. Takagi and Viessmann have been around for, what, 25 years as a real product of choice in the Northeast. And now they're pretty much across the country you can buy these products. So the challenge with these products is that, why do you think that guy's smiling? Is that Viessmann is worth like in the order of $4 to $6 grand, right? So I replaced my $700 furnace that actually is really easy to install, right? I mean, you literally just hook up the gas, hook up 115 volt power, and I bash some sort of tin together and put some duct tape on it if I'm a high performance guy. And boom, we're installed. With the Viessmann, I actually need like a skilled hydronic plumber, like somebody has to know what they're doing. And you even have to like use clean water and all this German shit. You know, you can't just put mud into it, it might not work. So, and that means that the actual installed cost on the boiler is likely to be something like 4 times what it would cost the furnace to produce the same output. Which, you know, that's not trivial. Now, for people who have money to do really good stuff, that's a great solution. Now, we also have a range of hot water heaters and combo hot water heaters. The boiler on the right is an instantaneous boiler with a small tank and heat exchanger to do both domestic hot water and space heating. And it's easier to install because you just plug it into a 115 volt power outlet, and then you have gas, cold in, hot out, space in, space out. So it becomes relatively easy to install. But we're still talking several $1,000s. This is about, in terms of value, this is probably one of the lower cost and higher value products. Its minimum output is 15,000 BTUs an hour. So that means that you can buy this product at $2,000 to produce half as much output as the Goodman furnace I showed. So, and it only costs you 3 times as much money. So these are examples of how the myth of reducing load saves you money. No, it doesn't. It costs you money. It costs you money. The real advantage of using these boilers is that you can actually store some of the heat in thermal mass in a water tank. So you can run it for short periods of time, store up a lot of heat in the water tank, and then meter that heat out over the next 3 hours as needed by the building. So the actual output of this, you could use this unit to meet a 1,000 BTU an hour heat load, no problem. So you could easily use this system if you had a tank to heat that apartment I talked about with 2,500 BTU an hour loads. But you need the tank to be able to meet these micro loads. If you try to use this directly, there's a pump in the bottom left corner, there's a pump. If you use the pump to actually deliver the heat directly to the space, the minimum output is 15,000 BTUs an hour. And that would cause immediately temperature overshooting in that small apartment. And actually a surprising number of houses. Here's another combo system. I'm showing this to give you a sense of the cost-benefit ratio. On the left, we have a $750 power-vented hot water heater, natural gas hot water heater. On the right, attached to a white-painted piece of plywood, is a couple of pipes and pumps, which comes from a local plumber, where I live, for about $600 bucks. And you just have to screw it to the wall and attach the PEX pipes. And so that provides you a hot water heater and a tank, and then you use the hydronic distribution system. Here's some just showing what's involved. There's a heat exchanger to take the heat from the domestic hot water and dump it into space heating. A mechanical mixing valve, so you dial in the temperature you want on the floor. Let's say you want 120 degree water in your floor. And basically there's a thermostat to run the pump on the floor, and when it gets cold, the pump turns on and it just runs and does its stuff. And it requires a 115 volt plug-in and 4 connections, 2 to space heat, 2 to the domestic hot water, and we're done. in this system, Andy asks, is the whole system potable? No, that's why there's a heat exchanger. So this is a system which actually has a stainless steel brazed heat exchanger to separate the water in the floor from the water you drink. And that's critical because in many jurisdictions you're not allowed to mix the two because stagnant water in floors can grow bacteria that can subsequently kill you. Apparently that matters to some people. Now, if you're in Vermont, it doesn't matter, or New Hampshire, it's live free or die, and sometimes people choose the latter. So that's why this is actually a more, I can take this $600-some board and reduce it price in half if I didn't have that restriction. And I'll show you one way to do that, sort of, in a bit. So, condensing boilers. We have to talk about condensing boilers to make them condensing. There's been a lot of retrofit programs in the last few years where there's been a swap the box program. They'll pay you to take out your old boiler and put in a new boiler. And the assumption of many of these programs is that if I take a boiler that's an old boiler rated at 75% and I purchase a boiler rated at 95%, I will have a 20% reduction in space heating. But that's not true. Because the only way you can get to a 95% efficient natural gas appliance is to have a condensing appliance. And you can't buy a condensing boiler, you can only build a condensing system. And what that means is that you need to have, it'll only get those high efficiencies if the water flowing into the boiler is at low temperature. How low? Well, lower is better. But 120 kind of would be nice. 110 is better as water flowing back into the boiler. If you don't do that, you will not get condensing and you will not get high efficiency. Period, full stop. You can't buy a device that will get 95% natural gas efficiency with water entering it at 140 degrees. So how are we going to get low water temperatures entering the boiler? Well, there's several different ways. One is you reduce the temperature that the boiler produces when it gets warmer outside. And that's called outdoor reset. By reset, mechanical engineers mean it changes. It doesn't really reset. They just say that to screw you up. So outdoor reset means that the supply water temperature adjusts, it varies, it modulates as outdoor temperature rises. So you might actually have your boiler set up to deliver 180 degree water when it is minus 10 outside. When it gets to 10 degrees, you only need 160 degree water and you can easily meet the space heating needs. As the temperature rises to 30 degrees, you might be getting away with 130 degree water. That's outdoor reset. To do that, you'd need to actually have a sensor outdoors. There are outdoor reset systems sold that don't have an outdoor temperature sensor. They don't work. Just FYI. So that's why it's sometimes important to understand these things so you know when you're getting screwed. Another thing that can happen is that you can actually move water at a variable rate through your heating appliance so that the water coming back always meets a certain temperature. So let's say I have a variable speed modulating pump. If the temperature of the return water is 120 degrees and it starts to rise when the boiler is running, I could increase the speed of the water so there'd be more water going through the boiler so the temperature would fall. And if the temperature got too low, well then I could actually slow the pump up so the water get hot again. Now this requires a pump that varies in speed and a sensor that measures the temperature of the return water. It really quite simple and straightforward, but hard to find. You generally have to make your own. And you know what happens when you roll your own. It's, unless you're in Washington or Colorado, it's a problem. As I mentioned earlier, the combustion is really efficient. It's just how effective I am at extracting the water. And let me explain a little bit more about condensing. When you have a condensing furnace, this isn't a risk because the air temperature entering that furnace is always cold, 72 degrees. And that means that when the hot gases from the burning of the natural gas pass over the heat exchanger, they're cooled down, and that will condense the water vapor that's in the natural gas. Because when you burn natural gas is CH4, methane. CH4, you add O2, that'd be the oxygen bit, and you create H2O plus CO2. That's one of the reasons natural gas is a clean burning material. It actually, theoretically, it's perfectly clean. And so it produces carbon dioxide and water. The water, of course, because it came from burning, comes off as steam. There's a lot of energy in steam, as most of you would recognize. And so to be able to extract the heat energy that's in that steam, we need to condense the exhaust gases. We need to condense the water that is in the exhaust gas. And to do that, I need to cool the air that is leaving the flame down to below maybe 120 or 130 degrees. That would be ideal. If I can cool the air down even further, I can extract even more energy. And so if I were to say take a condensing furnace and take air from 50-degree crawl space and move it to the furnace, my efficiency could be, on many of these standard products, will rise to like 98%, 99%. Because it's so cold, the air coming in, that it condenses more. And so the 96% rated product behaves as a 99% product. At the same time, if you take a non-condensing furnace and you use it in a hunting cabin in Minnesota, and you turn the thermostat down to 55 because you don't want to waste a lot of energy, a lot of propane. So now the non-condensing furnace has 55-degree air coming across the heat exchanger. It will now condense, and it was never intended to condense. So isn't that a good thing? Doesn't that get more efficiency? Well, it does get you more efficiency for a short time. But the impurities in the gas are primarily sulfur. And so when you combust it, it produces what's called sulfuric acid, which eats the shit out of metal. And so condensing furnaces are different than non-condensing furnaces in that their heat exchanger, the thing that separates the air from the flame, are made of really corrosion-resistant products. And if you try this in a normal furnace, in a hunting cabin in Minnesota, just as an example, it happened many times, by the way, it will corrode through the heat exchanger in no time, a few months, and you avoid the warranty. So you're tough luck. Well, yeah, if you happen to come in after a long weekend and then run the furnace up to 70 where it belongs, because of the holes in the heat exchanger, now you get to breathe the CO, and then you die. No separate tests required, yeah. It's pretty straightforward. If there's holes, you're dead. Now, maybe you don't spend much time in the furnace, in the cabin, but the problem is, again, you're going to be there in the evening, and that's when you're going to die, right? So the furnace is going to run at night. You're going to be asleep, so you don't know to get up to open the window for ventilation, and that's how you get CO poisoning, and it happens all the time. Don't do that. Now, furnaces have reliable condensing temperatures, but boilers, the temperature of the water returning to the boiler varies tremendously with weather and how the building is designed and operated. And as such, its efficiency varies tremendously. Unless you have a system in place that guarantees that the water flowing back is the same temperature all the time, your efficiencies will vary with weather and operation. And so you need to do something to make sure the water coming back is cold enough to get condensing. Boilers the old boilers that didn't condense used things like cast iron boilers, right? You heard of those things? You had to absolutely protect ever getting cold water back, because you'd get condensation and the sulfuric acid would eat through the iron and you'd fail your heat exchanger, and you'd spring a leak and it would be a very expensive repair. Pretty much the cost of the boiler. So we've moved to condensing furnaces and boilers which can tolerate condensation, but if we're going to get efficiency, we have to make sure that the return water temperatures or air temperatures are low. So here's a plot from the ASHRAE handbook, systems handbook, showing for a particular setup on the vertical axis, it's the actual efficiency of the boiler, natural gas boiler. On the bottom axis is temperature, starting at 40 degrees Fahrenheit, going up to 240. 40 degrees? What kind of boiler would you put 40-degree water into? Snow melt systems. Yeah, because energy is expensive and difficult to save, there's a lot of people who actually use boilers to melt the snow off their freaking driveways. And so in that condition, it's actually very reliable that the water flowing back will be at 40 degrees. And under those conditions, if you were to buy, just to name a brand, a Vitodense 200, you'll get something like 99 point something% efficiency. And the air coming out of the exhaust pipe will cool your hand. Pretty crazy, huh? Now, as we typically are putting water through radiant floors, the radiant floor, let's say, may have a return water temperature of 100. If it's a low load building, maybe 90. Then your efficiency drops off, but you're still into the mid 90s. And the air coming out of the exhaust pipe is warm, but that's it. As the return water temperature goes up, you'll see here the bottom temperature, it goes up to something like 240 on the rightmost point. But let's look at a return temperature of 180. My efficiency is down to 86%, which is about the limit. Why would I have a 160 degree return temperature? What would I be heating if I had a 160 degree return temperature? Baseboards, convector cabinets, and in many commercial spaces, fan coil units. They regularly are running at supply temperatures of 180, return of 160, and almost all of them are rated at supply temperatures of 190 and return of 170. And so those are the temperatures that actually burn dust and make it smell pretty funny if the dust is built up. So if you had systems like that, you're not going to get very high efficiencies. Well, you're going to get 80 something. That's not bad, but it's still not much better than a pre-condensing boiler or a pre-condensing hot water heater. And so that return temperature is key to getting the efficiency. So if you do a swap a box program and you take your condensing boiler and you replace the old boiler and you don't do anything to change the convector cabinets or the radiators, you'll get no change, not much of a change in efficiency. You have to then add outdoor reset or reduce the temperature of the water going out to the baseboards, which you can only do if you actually add super insulation. So in low load homes, it should be easy to heat them with 120 degree water that returns at 100 degrees, for example, just something like that, which means that we're now in the low 90% efficiency range. Not bad. Let's say I'm heating domestic hot water. What temperature is the inlet water for a domestic hot water heater? 45 in the middle of winter in this area, rising to like 55 to 60 as we move further south until you get to 70 where Andy lives. In all cases, it's on the low end here, right? So you are, in a domestic hot water appliance, it's really easy to get high efficiencies condensing again because the water coming in is cold. It's the space heating recirculate situation where you can completely screw this up and not get good efficiencies. So that's important. Yes, sir. Yeah, well, right. The question is, what are the rating conditions for AFUEs? Well, it's worse. It's more than just rating conditions because, for example, there's standby losses. So meaning heat that gets out of the cabinet when we're firing. If you don't insulate the cabinet, the heat goes into the boiler room. Now, how would you know if that's happening? Well, when you walk into the boiler room, if it feels warm, I bet you're losing heat. It's just a suggestion here. I think we should follow up the hypothesis. Another problem is that if you're talking about non-sealed combustion, I don't care about the AFUE. I care about the fact that the air is going up that chimney whenever the boiler is turned off. Well, and when we get to high efficiency ones, those problems tend to get less and less. And so the rating conditions depend on the inlet water temperatures, and it depends, well, I don't know the exact number they use. Do you know the number for the AFUE? But they do use low temperature water, but I think it's reasonable. Yeah. The 96 to 98 is a low water temperature return, but I don't know if it's 85 or 95 or something like that. But it clearly won't work when you put it on a baseboard system. Always. This is a heat exchanger to show you what goes on inside a boiler, a condensing boiler. half of those voids have exhaust gases going through them from burning the natural gas or propane, and the other half have water flowing through them. And that's how close in contact the water is to the exhaust gas, and that's how you get high efficiencies. Lots of close contact so that the water leaving is going to be warm and the exhaust gases leaving is going to be cool. So that should tell you a couple things about how you know whether or not the condensing boiler in your application works. When you put your hand over top of the exhaust pipe, if it's really freaking hot, it's not very efficient because it's throwing the heat away. So that's one test. The second test is how much water is coming off the condensate line. Condensing boilers have condensate lines, right? Because they produce condensate. If no water comes off the condensate line, how much condensing do you have? None. And so one of the first tests about checking whether it works or not is to actually take like a coffee can or something like that, put the condensate line in, and then run the boiler for a while and come back next week, take the readings off the natural gas meter. And if there's no water in the coffee cup, it wasn't condensing for the whole week. Then you measure how much water, if it was condensing, and you compare that to the gas you clocked in, and you can tell people what the rough efficiency was over that time period. But you know if there's no water in there, you're in the high 80s to mid 80s. And if you get if you get like an ounce of water per 1,000 cubic feet, you're basically high 80s. To get to the 98%, you're going to fill that coffee can up for 5,000 or 10,000 cubic feet of gas. And I don't remember the exact number, but you can look it up. So many thousand cubic feet of gas, if burnt properly, will produce so many ounces of water. Low. So Bruce Harley, of course, is telling us about retrofit houses. Just to repeat what he was saying, the kernels of wisdom there is that you don't really have to super insulate a house or do massive changes in most cases to get condensing out of a radiator type system. You can do an awful lot with controls, outdoor research and adjusting the pumps to be right sized and all that. You'll get condensing for large chunks of your winter, and maybe you lose it for the 10 or 20% worst hours. But even then, replace the windows, do some air sealing, and now you're down to 100% of the hours you get condensing. Oh, well, I'm going to show. We'll show you. You can design baseboard. New buildings is easy. It's just you have to do it, and you have to be aware of it. This is actually the Viessmann boiler showing on the bottom red line there is I would say even a lower temperature convector cabinet design. 167 supply, 140 return. That's a European standard temperature. We would probably do 180 supply, 160 return, and the efficiency would be even lower until you get really low fire so that you actually can take full advantage of the heat exchanger. But you can get pretty good efficiencies, and this is, Bruce, this is part of what you're showing. I mean, we would probably design an existing house somewhere between the 140 supply and the 167 supply. At design, with outdoor reset, you'll regularly be in the 100 to 125 degree supply, and then you get condensing. So we mentioned radiant panels often give you good efficiencies, like radiant floors, because the supply temperatures are low, return temperatures are low. Sometimes, if you want to be really clever about it, you can actually take the radiant floor and run it through the loop goes through the coldest spot just before it goes through the boiler, like a front foyer in a commercial building, or the snow melt system before it goes back to the boiler, and that way you actually get more efficiencies, because the key here is get that water temperature as low as you can make it. Fan coils, and we're going to talk, someone said hydro air system earlier on, fan coil units, hydro airs, if you want your condensing appliance to condense, you're going to have to make sure that you're designing for lower temperatures, not the 180 degrees they're commonly rated for. And baseboards, same thing. Okay, so let's now look at, we go from a boiler to a combo system. The problem with a furnace is it doesn't make hot water. That seems kind of obvious, right? But I mean like domestic hot water. So a furnace is a cheap and cheerful way to make space heating, but it doesn't solve my domestic hot water. And in a low-load building, residential building, domestic hot water is a big part of what we have to do. So one of the reasons why you'd pay for a boiler, always more expensive, is if you could also get domestic hot water, because then you got a twofer, right? And so I got both heating and hot water. Okay, so if you buy a condensing tankless, most of them have minimum load settings of 15 to 35,000 BTUs an hour, which means that they're not really a solution for the low-load house until you add some storage. So then you now are you're basically buying a tankless water heater with a tank. Now, I love ironies like this. I think they're quite delicious, is that it's taken America 10 years to figure out that tankless water heaters work best with tanks. And we're almost there now, and so we're actually starting to see tankless water heaters with in tanks that come right with them. But they put them in a box, and they're not circular, so it fools most consumers into believing they're tankless. So, I don't know, I'm glad I don't do the marketing for these people. It's very much a tankless task. So in terms of distributing energy through the house, the advantage of having thermal mass in a tank is I can now size, let's say, ductwork to only deliver 6,000 BTUs an hour. I can actually get a fan coil off the shelf that is rated at 3,000 BTUs an hour, 5,000 BTUs an hour, 15,000 BTUs an hour, or any number in between. So I can actually buy heating, quote-unquote, devices that can meet any of these low-load needs. And so that's one of the reasons why people look at hydronics in low-load houses. It's not because there's some sort of inherent superiority. It's because we can't buy product in furnaces that could actually do that. So we can kludge together a overcapacity tankless or boiler, add a water storage tank, then add a fan coil unit of any size I like. And so for, let's say I'm building fancy houses for rich people, and I want to actually provide a thermostat in every room. And yet, because I'm building good houses, each room might only have a peak heating need of 2,000 or 3,000 BTUs an hour, even the big-ass rooms that they have. Well, the way to do that is, well, hydronically, a fan coil in every room. And so when the thermostat in that room asks for heat, it is able to simply deliver 1,000, 2,000, 5,000 BTUs an hour, whatever you want. You design it. And you can buy all of those things off the shelf from multiple suppliers. And so now I have a room-by-room heating solution with a central heat production unit and heat storage unit. Because it's pretty easy to run a 3/4-inch PEX line through a house, right? So even if it is 80 feet away, it's easy to get there. Because you can thread it through the walls, you can fish it afterwards and retrofit. And that's another advantage in retrofit solutions. You can actually fish half-inch PEX pipe through walls without cutting open the walls. And so you can actually put individual heaters and coolers in rooms using fan coil type units. But anyways, we'll get back to more of that. Combo systems are called combo because they do both heating and domestic hot water. So this is an example from a drawing from Siegenthaler, who does a lot of hydronic stuff. Really good author to read. So on the top there we have our condensing boiler system. Then we have below it a storage tank, because we need some thermal mass, right? Because they can't make the boiler small enough to meet the needs that we might ask of it. Then I have a heat exchanger, so that Andy's question about how do I separate warm water that I use to heat the house from warm water that I shower over my body. And we have some sort of temperature control to get out to domestic hot water so we don't scald people. Right? So it's good not to give them pneumonia and kill them. It's better not to scald them and make them go screaming to the hospital, still alive, so they can sue you. It's really hard to preach Legionella disease and they die, but it's really easy to prove that they were scalded because you didn't provide temperature control. And then those lines go off to units. They could be fan coil, radiant floor, baseboards, coves, doesn't matter. So the difference between the boiler and the combo is they have a heat exchanger in them to transfer domestic hot water, the heat from the space heating system to domestic hot water. To make it work in a low-load building, you need a storage tank. Period, full stop. That's basically it. Low-load buildings, almost by definition, will require some storage tank to store the heat to meet low-load requests. The question there is a very astute one, actually. The comment is, you want us to have a low return temperature from my space heating to get condensing. And I'd also like to take advantage of cold water inlet from the street to get condensing. In most of these combo systems, that is compromised. That is sacrificed. Because the water tank is probably sitting at 110 to 120 degrees. And so you can't actually get as much condensing as if you accepted the return temperature at 100 and sent it out at 140 or something like that. And yes, that's true. And this is why you have to be careful. If engineers are designing for efficient systems, they can regularly screw them up. Because there is no way to well, there's tricks that we can do to reconcile some of that, but you have to be willing to sacrifice the 4% efficiency points to get a system that works. When we try and have our cake and eat it, you end up with trouble. I'll show you some other piping diagrams that get you some benefit, but it's a common compromise. So, when I have a boiler, or more likely in a low-load building, I have a tankless system which has a minimum output in the 30,000 BTU an hour range. I need to put a buffer tank between my system loads, which are radiant panels, fan coil, baseboard, and the boiler itself. And that size of that buffer tank depends on how much out of match your boiler minimum sizing is with the load that you're going to demand of it. So you actually need a slightly larger tank if you have a super efficient, let's say an apartment with a 3,000 BTU an hour peak load. You'd probably want a larger tank than if you have a 30,000 BTU an hour load house, which is pretty close to 30,000 BTUs an hour boiler. But if you can put a bigger tank in, why not put in really big tanks? Let me count the ways. So why? 1, they cost more. 2, they take up more room. 3, they have more surface area, so you have more standby losses. There's a whole bunch of reasons to avoid big tanks. From a performance point of view, we love big tanks. But from a everything else point of view, we hate big tanks. So it's a classic engineering compromise decision, right? You got to trade off what's important to whom and where. So rich people get bigger tanks than poor people, because the compromise on dollars is as important, right? Rich people have bigger places, so they can afford bigger tanks than poor people. In a 600 square foot apartment, they don't have as much room, so we have to figure out how to figure all that stuff in. So if you look back at this picture, this is I think that's another Wiesmann, with a combo add-on system on the below it. Here, they're trying to put these things in the living space because they don't want to even use up the room that a 24-inch diameter tank would have. And so that's when you get to those types of like small apartments, etc., these micro lofts and so on I was talking about, you know, that space really matters. And so if you can get small tanks to not use up space, it also saves you money and saves standby losses. It's all good. Another thing with domestic hot water, there has been a range of complaints. So here's some numbers I'll give you later on, but you might actually want to write this down. So the amount of energy that can be transferred by water is about 500 GPM times delta T. You know this off by heart, for God's sakes. So you don't have to write that down. Henry taught that to you? Oh gosh, I was going to say, I think you knew that before I was born. So that means that if I have 1 gallon per minute of water flow and a 1 degree temperature difference, I move 500 BTUs an hour. Okay. Now let's say I have a shower and some of you have suggested that would be a good idea. So I turn on my low flow shower head, which only draws a gallon per minute because I love the planet. And I live in Florida, and the water coming in is 70 degrees. And so I turn the hot water on, and now I have 1 GPM flowing through, and so I trigger my boiler. Okay, the boiler adds its minimum of 30,000 BTUs per hour, and so I actually now have the temperature coming out of the tap at 130 degrees. That would cause me third-degree burns in 30 seconds. So what do? Okay, add cold, but my shower fixture only does 1 GPM. So what do I do with the cold water I added to cool it down so to 105 or so, which most people want to shower at? You got to come up with something. I don't know. I don't have a real answer. I'm asking you. You suggested mixing it with cold water like every freaking body else. It's like the real option is, well, you dump her down the drain. This is what Henry Gifford would call, it's Newtonian physics. You can't square this circle. If you got 30 kBTU an hour going in as your minimum setting, and your flow is requiring only 1 GPM, I can't do anything with that water. And so what they do is they don't fire the boiler. You turn on 1 GPM, you don't get hot water, which is why they're now trying to get lower flow, lower capacity tankless boilers. And Florida is particularly the worst place for this because they have the highest water inlet temperature. You live in Quebec. And the inlet temperature in February is like 40 degrees. Now, not a problem, right? So the 40-degree temperature water being raised to 105 is 65-degree temperature difference times 1 GPM times 500, 32,500 BTUs an hour. Boom! Boiler goes on low fire. I'm happy. But until summer comes, when the water temperature rises to 55, and then the freaking thing doesn't work anymore. So, easiest solution? Don't buy low-flow shower heads. So install 2 or 3. George, Fritz, I mean, surely that's a solution that many of your customers use, right? You put in 5, 6, 7 shower heads. Yeah, 50-gallon per minute showers solves the problem. In fact, it creates a whole new breed of problem of how do I now get a big enough freaking boiler? So that is, and those are like real simple math. And again, manufacturers will sometimes pretend that they've solved the problem, but wait a second, you can't. It's basic fundamental physics is 500 GPM times delta T. So either you're producing less, the Navian, for example, is one of the lowest output boilers, tankless boilers, condensing, 15,000 BTUs an hour. So that's one of the reasons it works in places like Florida. But now here's the other thing is that that's a shower. Now I go into the, I don't have a shower, right? So I really want to save the planet, so I only have a shower once a month. But I am going to wash my hands. So I go in and I turn the tap on to wash my hands. Well, of course, the flow out of that tap, you know, I just turn a little bit of hot, a little bit of cold. It's nowhere near 1 gallon per minute. So I sit there and I wait for hot water. Doesn't freaking happen. So I open up the hot water a bit more until eventually I crack the 1.2 GPM in my example, needed to turn the boiler on low fire. And now the boiler pumps out instantly 120 degree Fahrenheit water. So I'm going, ah! Customers don't like this. Right? And so, and those are real life challenges that have come about because of tankless water heaters. It is the BTU, they say they're fully modulating, but they're not really fully. They're fully modulating down to a certain point. And unfortunately, much of the time we need them to be below that point. And so that's where we get challenges with tankless water heaters. So for those of you on the internet, use liquid hand sanitizer. Very practical solution right there. Don't need to worry about all this other stuff. Excellent. Thank you. Thank you. Yeah, and yeah, pays for the $200 window shade. Yeah. So That's part of the reason why we ask for these buffer tanks. If you, even at the lower end of the market, which is willing to put up with a fair bit of abuse, you're well advised to do a small buffer tank. And it doesn't have to be huge, because remember, I'm talking, if I go over with to wash my hands, I might only use 1 gallon of water total. And so I don't need a big tank of 120 degree water to wash my hands 3 times before the boiler ever once turns on. But what I do need is I need enough capacity in that water tank that when the boiler turns on low fire, it'll run long enough that it won't air out to heat that tank. So how big is that? 6, 12, 15 gallons. If it's a manufacturer product, they're actually down to 1 gallon. They're called a micro storage. They actually are able to control the boiler to only heat up 1 gallon of water. And that's intended for the hand washing and so on. And it also means that if I'm having a shower with a 1 GPM shower head, it'll turn on for 30 seconds and off for 30 seconds, on for 30 seconds, off for 30 seconds, and I don't notice a temperature change because there's this big mushy mass in between of a couple gallons of water. Now, do I like 30 seconds on and off? No, but the manufacturers figure it's worth it to avoid complaints. Put a bigger tank in, and it doesn't do any of that. Now, this is Armin Rudd's diagram from one of the reports that you can download from buildingscience.com. Our 10,009, I guess. It's 2010-09. There's been several iterations of this, right, Armin? And in fact, the biggest problem in this entire project was clogging up freaking strainers, which is not something that normally shows up in most of the drawings and so on. But if you take a look at this, this drawing, maybe it looks a little complicated, but really all it is a condensing tankless gas water heater, in this case a Rinnai. We've used lots of those. And you actually use a pump to pump water through the tankless water heater whenever the space heating says the tank has gotten cold. And the pump is sized to make sure that you get enough water through it so that the boiler can fire, heat it up, dumps the water into the tank, and the thermostat runs the water that comes from the tank to the space. So that thermostat, you could set it. In my house, I have a variation on this. I have a special thermostat where you can adjust the deadband to 0.1 degrees Celsius, which is 0.2 degrees Fahrenheit, which would be insane for any other heating system. But this one, it can go, I can hear it go click, click. It'll run for 30 seconds, turn off. Run for 30 seconds, turn off. Because all it's doing is turning the pump on and moving a little bit of heat until the thermostat is met, turns off. And so you can actually have very fine control because the buffer tank doesn't care that you're only dragging out of it 500 BTUs at a time. You just turn the pump on, turn the pump off, turn the pump on, turn the pump off. Now with a normal deadband, that pump will run for a couple minutes and be off for half an hour, something like that. But when the tank finally gets cool enough from having done its job of distributing heat, then the thermostat turns the big pump on that sucks the water out of that 6 to 12 gallon electric water heater and blows it through the hot water heater, and then it raises that 6 to 12 gallons relatively quickly in a few minutes, unless there's a concomitant draw, and then it shuts off. Bruce? The comment was, it says electric water heater, but my assumption is the electric water heater is not hooked up. That's absolutely correct. You wouldn't want to do that. Right. In fact, sometimes, I mean, I think you just disconnected it, right? You didn't unscrew it? Right. So I'm sometimes concerned that we should actually unscrew and put in a plug because, you know, if there's an electric connection, someone's likely one day to go and hook it up and then ruin the whole thing, but I don't know. Right, right. That's true. So you can see there's a mixing valve to control temperature so the domestic hot water doesn't get too hot. And the comment about I'm limiting my condensing, you're right, you are. The way this is plumbed in the current version, which is not the same as actually on the report, I don't think. I think it's changed, is that when you open a cold water tap and water is able to flow through the tankless water heater at a high enough flow, you can get condensing. And so this is one of the plumbing tricks you can use to try and say, if you open the tap up, you might get enough flow through the condensing water heater to turn it on, and under those flows, you do get really good condensing. But you do pay for condensing efficiency in this setup. Armin, do you want to make a comment?
Yeah, that is the way it is. You have to let it draw. It's going to pull cold water first, and then send it back to the tank. So it will get the cold water. And the improvement is that you'll be able to use that 140, 130, and then you get a, say, a 15 drop or right on it, and then put that back.
So as plumbed up, and I think I have a picture here. I think this is a picture right here of that installation in Utica, New York, thanks to NYSERDA and Building America. But that tank, you can see, Bruce, in the bottom left corner there is a relatively small electric tank because it has the right connections at the right price, and it's insulated. Commodity product, people can afford this. Can I buy that tank, a better version of that tank, from someone like Baxi or Viessmann? Absolutely. Just pay an extra $1,500 and you can have it in the right color. Armin's a bit more practical than that, and so we're happy with the $200 product right there. This can, but it still will never give you the 96% efficiency or 98% efficiency, but it works, it's cheap, it's simple, and it's robust. Yes. So the question was, if you use all the heat from the floor, is there any obstacle to that? Nothing except cost. And we're going to talk about radiant floors and why they don't work as well in low load, but they absolutely work. But it doesn't really help much because we have this stored tank. And the advantage of a radiant floor is that the radiant floor is itself radiant mass. It's thermal mass. And so it takes, you won't short cycle with a radiant floor because there's so much mass in that 1.5 to 2 inches of topping with 1,000 feet of tube that you'll always run the boiler long enough. You might overshoot a bit on temperature, but it won't be bad. But it doesn't solve your domestic hot water short cycling problem, which is the real one. Meaning the turning the tap on a little bit, the radiant, because you're separating the water on the floor from the water on the domestic. So one way to handle that is to actually have a separate heat exchanger that runs the floor, and then one that has a little buffer tank going to domestic hot water. So you can, I don't have a drawing of that, you can plumb radiant floor and domestic hot water separate. The radiant floor is its own thermal mass and gets you really good efficiency. And the domestic hot water, you lose a bit of the efficiency unless you exceed the 1 GPM whatever breakpoint. And so that's pretty close to the best you can do with a combo. And you're going to lose a couple points off of what you would if you had a separate domestic hot water heater and a separate radiant floor. Where's the question from? Yeah. So Gord Cook from Building Knowledge was saying that we have a fair bit of experience in doing this in semi-production settings. You know, whether it's Chicago or Houston or whatever. And Gord, you've got tons in really nice, actually, packaged projects in Ontario. And what's maddening to Gord, and I understand the maddening, is that depending on the mixture of dead bands of the thermostat, size of the pump, flow resistance of the tankless water heater, and the type of heat that's radiant or fan coil on the side, you get different performance, meaning you still can have problems. You can still get comfort, cold blow problems. You still get, comfort complaints, annoyance complaints. And so that's why I think that, Gord, is just a symptom of us not actually yet fully understanding the part load performance curves of every one of the components, from the mixing valve to the tank to the fan coil. And you're right, that right now this works, and Armin played around with it until it does work, but you can't just willy-nilly throw in anything you want. You're going to have to play with this to get this to work right. So hallelujah to you, right? I agree. So here's a, I happened to be in one of our wholesaler, HVAC wholesaler guys, and he had this in his office. I suggested I would never buy a product with that large of a hole in a water tank, but apparently I was missing the point. And the point is that there's a lot of insulation in this. So one of the disadvantages of a standby tank is not just the low temperature condensing being reduced. It's also that I now took my tankless heater and added a tank, and so I have standby losses because I got 120, 130 degree water in there anyway, and it's sitting there waiting for it to be used, and so there's a heat loss. But we have a pretty good solution to heat loss, and that is insulation. And it seems remarkable that this is a massively innovative product because they doubled the thickness of insulation in the water tank. Ooh, you know. But apparently in the mechanical business, this is a tremendous innovation. And so it really does work well, though. I mean, the standby losses for these things are quite small. Small tank, nice shape, very well insulated, costs money. But again, let's say you're doing a high-end, small, energy-efficient home, then that kind of product would show up. So we've had lots of these issues with combo systems and trying to match pumps to boiler, make sure that the cold water gets in at the right time, get the heat exchangers sized right, and all this stuff. One of the answers to the industry who made tanked water heaters to the condensing tankless water heaters was that, oh my gosh, apparently this expensive product called a tankless water heater, people are actually buying it. You know, they were quite taken by surprise that their $400 piece of junk was losing market share to tankless water heaters that cost $1,500 bucks. Because of course no one will ever pay for efficiency and comfort, and that's why they continue to make $400 water heaters. Well, once that market started developing and they said, geez, people are spending like $2,000, $3,000 on condensing tankless water heaters, they said, hey, well, we could make a condensing water heater and it would actually be cheaper and simpler. So they finally did. And so what we have now is at least 3 products out there. This is the State new Force, it's called the Force 90. It's only 90% efficient, and partly for the reasons that you're talking about, is that the cold water on the coming in is stored in the tank, and so you don't get the full condensing benefit. But it has a relatively large heat exchanger. The nice thing is you buy a tank, which you attach gas to. You plug into a 115-volt power outlet to get the power venting. And then you attach water lines into the domestic hot water for both space heating and domestic hot water. And that's it. You don't have to select pumps. You don't have to have a separate control to run the pump to top up the tank from one that takes heat off of it. It's like the simplest kind of installation, right, Gord? I'm not making it. It's pretty darn simple. It adds a T to the normal domestic hot water installation system. It isn't the most efficient. You lose a few points. In terms of cost, these are in the $2,000 range, $2,500 range. And when you use it for both space heating and domestic hot water, it actually comes pretty reasonably close to buying a furnace plus buying a domestic hot water heater. And yet you get the benefit, you get higher efficiency on the domestic hot water and lower on space heating, right? Because that $700 furnace gives us 96% efficiency. But we don't use much space heat in these houses. We're as much worried about domestic hot water. So if I can take my 75 to 80% efficient hot water and push it to 90, and I take my space heat from 96% and drop it to 90, I won, right? That's going to be win on the total energy. And it's simple, uses less space. It's got to be something that's appealing to that. So right now, in the last year to two, this has been a recommended solution for a lot of low-load projects where a furnace was going to cause too much of a problem and they could afford to upgrade their domestic hot water system. It's still a bit more expensive than a 75% direct vent domestic hot water plus a cheap furnace, but it's not much more expensive, and you save some space. Now, of course, this only makes the heat. We still have to attach it to a fan coil unit, right, to be able to get the heat out of it. This one on the left, the Rudd Advantage, is kind of an interesting product. It's meant for commercial applications, stainless steel, only 45 gallons, so it's a smaller. It has a 100,000 BTU an hour input. It's 95% efficient, and as opposed to 76,000 BTUs and 50 gallons and 90%. So on the left-hand side, it's a good product for a higher-end product. Either people who want more showers, they're telling you, I live in a passive house, and it's really energy efficient. It's 3,800 square feet, and I want to have 2 showers going at the same time while I'm doing my dishes. Okay. And so that kind of product there on the bottom left would do that. It'll provide space heating very easily at very low levels, and when you insist on having 2 showers at the same time while doing your laundry, this will also do this. So that kind of system, and it doesn't take much room, and it's made of stainless steel, so clearly it belongs in a passive house. The only disadvantage is it's made in America, and we wouldn't want that. So when we get to dumping heat into a building from a tanked or tankless water heater, as long as the water lines are all potable water and copper coils, to answer Andy's question, I don't actually have to put a heat exchanger between the two. That's mostly what we call hydro-air solutions. And so there's a pretty significant economic and simplicity benefit to being able to do that. So if you're running through a copper coil, you can literally just put a T off your hot water heater and take it over to an air handler. Now, when this was being developed, I think Bigelow in Chicago in the early 80s was the first guy to do this. There was no rules, but you'd buy an air handler and you'd buy a pump, and the thermostat would run the pump. Now that there's a bigger market out there, you can buy from several manufacturers as cheap and dirty as First Company or Rinnai matched to their system that has a built-in pump and coil, and they control the fan, the pump in sensible ways right out of the box. So if I buy a unit like this, and then I attach it to a unit like that, that is my turning hot water into air. And again, it's just attach a thermostat, plug it into a 115 volt outlet, and we're good to go. So what does it do that's anything special? Well, one thing is that they turn, when the thermostat calls for heat, they turn the pump on first before they turn the fan on. And that's because if you turn the fan on at the same time as the pump, air immediately goes across the coil and it's not warm, right? And so you get the initial blow of air that's at room temperature, and when air is at room temperature and blows on you, it makes you feel cold. So lots of comfort complaints are due to, oh, it blows cold air. It's like, well, no, it blows room temperature air, which makes you feel cold. And they're saying, like, I'm not here about semantics. I'm going to sue your ass if this doesn't go away. Right, okay, I understand. And so you want to be able to run the pump to warm up that coil for about 30 seconds before the fan kicks in. And so when the fan kicks in, you'd also like it to start off low, right? So nice and slow, so it picks up a lot of heat, warms up the sides of the duct so that by the time it dribbles out of the vent, it's actually warm. And then it slowly goes faster, and then you don't get people complaining about cold blow. So that's what a fan coil unit like this, and look, although they've been making these for several manufacturers for 25 years, there's a patent pending on the Rinnai one for something that probably has to do with like the crink in the metal or something. I have no idea. Nothing very useful. This is a fan coil unit run off of a hot water heater. This was how I ran my own house after I first renovated it, was fan coil unit using the electric hot water heater, because that way you can measure the energy input into the house accurately, right? You just measure the electrical energy and you got it all. And this, coupled to a very fine deadband thermostat, the temperature stays very, very stable. If you look closer at this, designed for the purpose of hydro-air, on the right-hand side photo at the top, you'll see a red Grundfos pump in there. And so that's all that the thermostat basically turns on that Grundfos pump to run it. Run the pump, sucks water out of the hot water heater. Then 30 seconds later, the ECM motor in the fan slowly ramps up. And it turns on slowly because people notice the noise when it turns on with an abrupt change. But if it slowly creeps up on them, people don't complain about noise. I'm not making this up. This is important. And so the slow ramp up means people are happy. And this one further has a built-in timer that for the first 7 minutes, when there's a call for heat from the thermostat, it runs the fan on low speed. And so the low-speed fan means it's A, quiet, and B, it doesn't use much electricity to run the fan. So 45 to 50 watts in my case. Moving about 400 CFM of air, and that allows me to heat at 15 to 16,000 BTUs an hour. Now, if the thermostat is not satisfied in that time, then it'll ramp up to higher speed. But in a low-load house, that'll almost never happen. Actually, the only time it happens in my house is when I have a setback to 65. You come home after a weekend away or something, maybe you're at Westford doing seminars or something like that, and then you turn the temperature up, and of course you're trying to warm the house from 65 to 70, then it goes to high speed. But generally, and because it runs at low speed almost all the time, it is virtually silent. So relative to like radiant floors, having lived my previous resident having radiant floors, this makes no more noise than radiant floors except on set up. But of course, I have the ability to do set back and set up really quickly with this system, unlike my radiant floor system, which took forever to set up and to cool down because of the thermal mass. Now, the reason this, like I said, it uses about 45 watts when it's running on low. It jumps to 150 watts on high. And when I put it on recirc mode, it draws 35 watts. Comes with a 4-inch pleated box on the side for filtration. You'll see the labels of input and output. It's like really quite simple. And it literally has a 150 volt plug on it that you plug into the wall. The reason, pretty heavy gauge cabinet, I mean, people don't use these very much because this is almost $1,000. 850 bucks or something like that. So clearly that's out of the league of most people who design houses, and so we don't use these very much. This is Ecologix, E-C-O-L-O-G-I-X, play on words. I don't know if where Lloyd Hunt went, but Lloyd had used some of these from Ecologix. And the thing here that we have to worry about is that even if I have this tanked or tankless plus tank system, is you want to keep the temperatures low for efficiency, but you don't want to get so low that you get complaints with cold drafts. And this has been a common challenge in hydro-air fan coil systems of all type. You want to make sure that the heat that's provided is warm enough when it hits somebody that they don't complain. That doesn't mean it has to be 140 degrees. Actually, we're regularly at 105 and 110 and you get away with it. But the bigger distinction is not the supply air temperature, which people think. The bigger problem is where are your supply air registers? And if you have the supply air registers on the floor, you know, like in the dirt drain configuration, so if you put them on the floor, the odds of somebody, like let's say I'm wearing a dress and I'm walking by or sitting next to the register, well now I get cold air blowing up my dress. Well, that's going to get you a complaint. Now, when it's fully in operation at 105 degrees, you might get away with it. But actually, you know, grandma probably doesn't even like 105 degree air blowing up her dress. Whereas when you do high sidewall vents, you know, you go to the middle of the house and you blow to the outside and you put them above people's heads, like at 6'8" and higher, then you actually can get away with lower temperatures. And the same rule is going to apply when we start talking about heat pumps. Is that they also produce low temperature air, relatively speaking. And so registers on the floor work in a world of 130 degree air, 140 degree air. And they turn on and people will go, okay, I'm being blown on, but at least it's warm air. But as soon as you reduce that temperature, people don't want to have air blown on them. They don't feel comfortable. So it is as much about relocating registers to up high than it has to do with what the temperature of the air is. So why don't people want to have registers up high? Can't sit on them. Heat rises. Heat rises. And so that's the normal, was that Well, you can't like supply heat in the inside wall of a house because heat rises and the heat's being going out the wall. That's true if you have a shitty house. Now, as soon as you actually have good insulation, air tightness, and most importantly, good windows, low E argon type stuff, actually that's not true anymore. And that's the paradigm shift that we have to make, is that as soon as you go to good houses, yes, those high sidewall vents work in heating mode. In fact, because they're high sidewall vents, they actually prefer to have the air temperature not too hot. You're better off with 105 degree air than 140 degree air because it's more likely to mix and entrain with the room. So don't try this with an old clunker because you'll have a higher proportion of comfort complaints. But if you do it really a well-done house, or I mean, anything like net zero energy or passive house, no brainer that it works. Bruce. Right. So unlike shrinking ducts, which doesn't save you too much money, actually shortening duct runs and fittings, elbows, and trying to get them out to the outside of the house, that saves money. That can pay for a decent air handler with an ECM motor, just reducing the duct runs and stuff on a medium-sized house. Another question, comment? So does the same sort of thinking of air distribution apply to HRVs? Yeah, in cold climates it certainly does, because an HRV doesn't supply air at 105 degrees. It supplies it like at 60 degrees when it's cold outside. So you sure wouldn't want to, like, blow it up someone's skirt. And so, yeah, you actually have to think quite carefully about where you put those vents. And the normal solution is to try and take that 60 degree air and mix it very quickly with room air. And the advantage of an HRV versus a space heating system is that you don't have as much CFM. So you may only be dribbling 15 CFM into a kitchen and 5 CFM into a bathroom. And 5 CFM of 60 degree air you can very quickly mix and get to a comfortable temperature. Whereas if you're delivering 50 to 75 CFM into a master bedroom at 105 degrees, you're more likely to have problems. That's what, but there's the same principle. It's just the degree of the problem is less. Sir, yes, at the end. I have not yet integrated all of this into a typical AC system, but I hope it's pretty clear how easy that would be. You would add a coil to this for air conditioning, and you'd add and I know this one here, ready to go. The comment or question is that you would have different controls when you added AC? Yes, so if you get an AC air handler of anything but the lowest commodity grade, it already incorporates slow starts, ramp ups as they call them, and low speed with a delay setting of various types. And so it's usually not a conflict when you add air conditioning to this. And that's part of the reason why air conditioning comes after, is that actually a lot of the challenges are in terms of the heating, and then once you've got that fixed, adding AC is relatively straightforward. And you can buy from Trane or Carrier or Goodman an air handler that has all this built in, which is, I thought, good news. So, before lunch, we just looked at boilers producing hot water and furnaces to produce hot air. Because boilers often produce domestic hot water, I introduced the combo system. And frankly, that's one of the winners in terms of low-cost, high-satisfaction solutions, is that tanked condensing system with a good fan coil. That provides heat, domestic hot water. You add on an air conditioner, and you've got air conditioning as well. and we've got a lot of this solved. Problem with that is that we still have ACs are too large. AC doesn't dehumidify. So does that make sense? That's sort of where we are right now. Now, let's say that I could get a modest-sized AC, or I was in a climate that needed 1.5 tons. How could I combine a hydro air unit to provide humidity control with a air conditioning unit? Because what the problem is when the air conditioner runs to remove humidity, it also cools. So I need to find a way to add heat back. So how could I add heat back? I could use the hot water coil to put hot water through. The problem is that that's not free heat. It absolutely technically works. In fact, it's a slam dunk solution. It's how we control our lab building at the university to exactly the relative humidity and temperature we want. We run the air conditioner to get not by temperature control, but by humidistat. And then the thermostat runs the fan coil to warm it back up, and it just pegs the temperature. The humidity runs as long as it's needed till the RH drops. At the same time, the fan coil unit is dumping heat in to keep it at the right temperature. But don't tell the code official. So what we need, of course, is a way of taking the heat that we're taking out of the air conditioner and dumping it into that hot water. That would be nice, and maybe we could go and leave the continent and find some solutions like that. And we'll look at that after lunch. The exciting shit comes after lunch. But we actually have some of the pieces now to start building the whole solution when you tack on an HRV to doing everything. Filtration in the air handler system, dehumidification by some sort of reheat, air conditioner, all that stuff works. Okay, heat pumps leading into air conditioning. Heat pumps are devices that pump heat. I know it's shocking given the propensity of mechanical engineers to use weird language. A heat pump is actually something that pumps heat. Now, in an air conditioning system, it pumps heat from inside to outside, and therefore it makes the inside colder. In heating mode, which for some reason we've also called a heat pump, we pump heat from outdoors to indoors. Like, I don't understand the question. So why that would be confusing. So people are sometimes going like, yeah, but how do they get heat out of the cold air? Well, I mean, it works in your freezer, right? Have they figured out how to actually make your freezer operate at 0 degrees Fahrenheit when it's 75 inside? In fact, they're commodity products, really cheap and cheerful, blah, blah, blah. So do you think we could maybe do the same thing and actually take heat out of like 0 degree outdoor air and move it into 75 degree indoor? Yeah, using exactly the same components and exactly the same people are there. You know, the Danfoss, the Copelands, the Emersons, they all make the same stuff. It's just some of us get to use it in the building and sometimes they just won't let us. You know, so that's the only difference. That we don't have product, it's not that the technology isn't there. So once we got something that pumps heat, kind of cool, or hot, depending on the direction, then we have to ask, where's it pumping heat from, and where's it pumping heat to? The from is called the source, the to is called the sink. So where's the source? Well, we could use the air, we could use water. Make sense? We could use the ground. We could use groundwater. So if I were to have a heat pump that pumped heat from air to water, we would call that an air-to-water heat pump. If we were to pump heat from the ground to the air inside the house, we'd call that a ground-to-air heat pump. Unless you were in marketing, in which case you'd call it geothermal, because it sounds like, well, shit, that means Mother Nature loves me. You know, it's like free heat welling up from the planet, giving us, you know, energy, which is why, of course, geothermal systems are so inexpensive. So the labeling, though, should be correct so we don't get confused. Now, some ground source heat pumps actually are connected to a pond or something like that, in which case they're not pond. They don't call them pond source, but they're water to air. Now, if you don't want to heat your building with air for some of the reasons we talked about in modulation and needing storage, you could do water to water, or groundwater to water, or air to water. It's all should be really clear. And heat pump doesn't say which direction it moves. People sometimes think heat pump always means it heats that building. No, heat pump is a heat pump. And it's just air conditioning is a very special subset where the heat pump is air to air from indoors to outdoors. That's the exception. Heat pumps are actually general, and we should understand them. Okay. Now, ideally, we wouldn't just be able to deal with heat from the air or the water in the environment. We could take advantage of waste heat, which in residential is hard to do, actually. We don't have a lot of waste heat to harvest at one spot. But as an example where this is becoming common, let's say you run a business and you have like a server room. I know it's a pretty rare scenario, a little niche market there, that you might have a server room with a whole bunch of computers and switches and stuff, which of course is going to be really hot because it's a server room. So you could actually take heat out of that server room and put it into, for example, water. So a water-to-water heat pump there with a fan coil in the server room, dump the heat into your domestic hot water tank would be one solution of waste heat. And in fact, that's very common in low-energy commercial buildings. So that would be useful. Or I could take heat out of the basement in the summertime and use it to dehumidify the air, and then I could take the heat and dump it into my hot water heater. That's called a heat pump hot water heater. So, there's options. All of these are just heat pumps, and many of the components are the same. So all of them use compressors. In the old days, we said they used Freon, but we don't use Freon anymore because it eats holes in the ozone layer, and we end up with Blade Runner. And so instead, we've switched several times to different refrigerants. The first, it's just like we heard yesterday with blowing agents for foam. They're actually very closely connected. The blowing agents first went to low ozone depleting, and then they're now moving to low global warming potential, both ozone and global warming. And the movement is they're creating these refrigerants in heat pump systems that will also be like the blowing agents we saw for the spray foam. An alternative solution that's being bandied about is CO2 as a fluid to use instead of Freon. The biggest problem with CO2 is it's free. No, sorry, that's not really the big problem. The technical problem is that you actually need a lot of pressure. It's a really high pressure system, and therefore you need better components and tighter tolerances to make CO2 work. But there are lots of CO2 systems coming online because the refrigerant is like, people are paying you if you'll buy CO2 from them, right? How many million tons would you like? I'll give it to you. Like, I'll even pay you to take it away. And so we can use those as well. But today we tend to use R410, right? R410A is the most common in air conditioning systems. That product was designed for air conditioning systems, and it doesn't necessarily work as perfectly for heating. And it works very poorly for hot water heating. Each gas has a range of temperature it can work at. So our Freon, R12, wasn't very good at heat pumps. It couldn't get the temperature hot enough. R410, well, you can get it higher, but there's limits. You can't make domestic hot water with it at a temperature of 140 degrees because it'll actually break down. 410 will break down. And so if you get a hot water heater, a heat pump hot water heater that makes water that's hot, like 140 degrees, it'll have a different refrigerant in it. Often 137, like the stuff we have in our cars, because to get an air conditioner to work in Death Valley, you need to use a different refrigerant. And that's a requirement for the air industry. So, and there's also 507 that you can get in Europe, 504, that make high temperatures, but they don't work at low temperatures. So right now, 410 is a good choice for us, but in the future, we're probably going to see more of the R744, which is CO2, which not only does it work well at minus 40 degrees Fahrenheit, it can also make water at 180 degrees Fahrenheit. The price being you have to make more robust compressors and pipes and such. But it can work over that entire range, and it's kind of like a bit of nirvana for people who care about this stuff. I care a lot about this stuff because I really have no friends other than Joe. And you can see why that would mean I would spend a lot of time doing anything but. So our basic fridge is a heat pump where we cool the indoors to 40, and the back of the fridge is going to be somewhere at 95. And that has a COP, a coefficient of performance, of about 3 to 1. And they've improved the efficiency of fridges a lot in the last 25 years, mostly by what? Insulation. Yeah. So in the history of efficient appliances, refrigerators are often brought up, but 80% of the improvement was delivered by insulating. And the rest there was an improvement. In the 1970s, the COP of these compressors was in the 2.3, 2.4 range. Now they're in the 3 range. And if you buy top-of-the-line stuff, we're doing 3.3. And so there are still some gains to be had in the compressor, but really it's like make the insulation thicker and you're pretty good. Your typical, here we have a air conditioning system set up on the left-hand side where the coil on the outside is at 135 degrees so that when I take 95-degree air and blow it over, the heat goes from the coil to the air and I reject heat. And inside the heat pump, if I have a really nice system, the coil might be 40 degrees, and so as air from the house at 72 passes over it, it gets cooled down to 55, and hopefully lots of water condenses on that 40-degree, 45-degree part of the coil and drips water out. And so that's a typical air conditioner, which we have in the majority of American homes. We both have a fridge and an air conditioner, 2 heat pumps that are available. Now, it's hard to find small air conditioners unless you buy a fridge. Because fridges are actually, you have all the components necessary to make a small air conditioner. And the same people who make the Copeland scrolls in your air conditioner make the scrolls, well, there are more rotaries in the fridge. But they don't want to like build you a small air conditioner because they don't like you. That's the best answer. It's really more about the retrofit market again, right? The retrofit market's looking for 2, 3, 4, 5-ton systems, and the new market isn't very big, so why should they build a 1-ton system? Even though it's trivial, off-the-shelf, trivial components, anybody could mock one up themselves, but there's no market. Well, window air conditioning units, which was mentioned as and they are, like for $100 you can buy a 6,000 BTU an hour made in China window unit, which has all of the necessary aesthetic and acoustic characteristics necessary in Foster's next $5 million house. Room by room control, what's not to like? And so you're completely right. And actually, I know numerous people in this crowd have probably heard the argument made that if you're doing an apartment building in New York City, the most energy efficient air conditioning system is just to get a window shaker. As long as you're willing to overcome the acoustics and aesthetics, it's true. They really are good solutions. And it just shows how wanting the manufacturers are in delivering the needs that actual people have of, can you sell me an 8,000 BTU an hour, 15,000 BTU an hour central air conditioner? Yeah. You have a low load house, cooled all last summer with a 6,000. Small. Yeah, it's small. And the shocking part about using 6,000 BTUs an hour to cool a 1930s 1,500 square foot bungalow is that, well, what would Manuel J tell you needed? 2.5 tons, eh? Interesting. And of course, I don't know where Chris Schumacher is, but when he got his air conditioning installed in his house, we didn't do a Manuel J. We did an hour-by-hour energy simulation to account for all of the shading of the houses next door and all that. And so you end up with this 60-page printout in living color, and you go to the installer, and you're going, yeah, I'd like to buy a 2-ton air conditioner. And the guy goes, nah, you need a 3-ton for that house. No, you don't understand. I have advanced degrees in engineering, do this for a living, and I just did an hourly energy simulation to get exactly the peak loads I need, and I need a 2-ton. I don't know. I think you need a 3-ton air conditioner. It's like, oh my God. You know, so there is a huge challenge with just getting the sizing right, you know. And the nice thing about the 6,000 BTU/hour window shaker is that we can actually install it in the room which has the comfort problem. For example, the bedroom with the window facing west, you care about that room being cool because you're going to sleep in it, and the sun is just baked in it all day. So when you get there, it's like the hottest. You can put it there.
My temperature variation without putting the air about 7 degrees where it was.
Right. So 7-degree delta, which wouldn't meet the ACMA standards. Right. That it's perfectly acceptable and comfortable temperature variation, but it doesn't meet the rules. So just to understand a little bit more about heat pumps, because I want you to have something to work up your appetite before lunch. There's this French guy called Carnot who did the thermodynamic fundamentals of heat pumps. And if you look at this chart here, the blue line with the diamonds at the top is the theoretical maximum efficiency, COP, that I could get if I were to change the temperature. The way you measure heat pumps, well, the efficiency of heat pumps varies with the lift, it's called. When I pump heat from 80 degrees to 90 degrees, that's a 10-degree lift. If I want to pump from 20-degree outdoor to 90-degree indoor, that's a 70-degree lift. And if I want to go from 20-degree outdoor to 130-degree water, wow, that's like, I forget what I said, 20 to 130, that's a 110-degree lift. And so those are the efficiency drops, according to Carnot, according to the blue line there, is that the COP is limited to between, well, at low temperature lifts, not bad. For air conditioning, you should be able to get 8 to 10 COP, and we're delivering products that are in the 4 to 5 range. And for heating, when it is really cold outside, like 0 degrees heating out, 0 degrees outdoor temperature, heating up to 80-degree air, we should be able to get COPs in the 5 to 6 range. And here's a plot of a bunch of products. One is a air-to-air heat pump from Goodman. One is a Trane water source heat pump. And another is a ground source heat pump from Next Energy, which is basically the guts of a water furnace with a different shell around it. And the COPs, as you get to higher lifts, drops. That's just a key rule. As you try and pump higher differences between temperature, the efficiency drops off. Which, Bruce, is why I mentioned the SEER rating using 82 degrees outdoors and 80-degree return as a joke, because the lift is so small. 2-degree lift, yeah, I think maybe we can pull that off. In fact, most of us could probably ignore the 2-degree temperature difference and just go with it. But we're actually using more than that. In air conditioning mode, we tend to be 10 to 20-degree lift. In space heating mode, we tend to be as much as 80, 90-degree lift, depending on how cold the place is that you live in. So the real challenge in space heating with heat pumps is that large temperature lift. If you live in a place like, let's say you live in Houston, where cold weather is called 45 degrees, or, okay, 35 degrees, you don't need much of a lift to heat the house, right? 40, 50 degrees, that's easy. But if you live in Vermont, then you now need a much different technology to be able to get there. So we're going to look at that after lunch. Okay, so we're breaking for lunch. I'm assuming, unless somebody who is an adult knows differently, we're eating downstairs below where we, like same where we were yesterday? Uh-oh. They changed it up, Joe.